Hi everyone. Welcome to my presentation today on Supply Chain Network Optimization for Manufacturing. My name is Mohammed Shakib Ali Afani. Glad to have your attention. Manufacturing supply chains often struggle to balance cost reduction with meeting customer demand. This project addresses the challenge by optimizing production, inventory, and distribution across multiple echelons to ensure timely delivery, cost efficiency, and effective resource use. The primary objective is to minimize total costs across the supply chain. This includes production, transportation, and inventory holding costs. Another key goal is to satisfy customer demand consistently at retail locations over several time periods. Lastly, the model aims to maintain optimal inventory levels while preventing capacity bottlenecks that could disrupt the flow of goods. This model is formulated as a mixed-integer linear programming (MALP) problem and implemented using Python with the Gurobi optimizer. The data includes production capacities, transportation costs, holding costs, and demand forecasts, aimed at minimizing costs while meeting supply chain constraints. The model involves decision variables representing production quantities at factories, shipment quantities from factories to warehouses and retailers, and inventory levels at warehouses. The objective is to minimize the total cost, which includes production, transportation, and inventory holding costs. The model is subject to several constraints: factory production capacities, demand satisfaction at retailers, inventory balance at warehouses, and flow balance between production and shipments. The Python code structure directly mirrors the mathematical model, ensuring a seamless translation of the problem. Gurobi efficiently handles large-scale, multi-period constraints, optimizing the solution. The output includes optimal quantities and cost minimization results. Additionally, the model is designed to be modular and can easily be adapted to different network scales. Results. The model identifies optimal production and shipment quantities for each period. Inventory levels are adjusted to balance cost and demand, ensuring efficient operations. The total cost is minimized over 3 periods. Key insights include improved supply-demand matching and a clear distribution of costs across production, transportation, and inventory. We analyze the impact of varying demand levels across time periods to understand how fluctuations affect the supply chain. Additionally, we explored capacity tightening at factories to test the robustness of the model under constrained conditions. Finally, we compared the total cost under different demand and supply configurations to assess the model's adaptability and cost efficiency. We also assessed the impact of changes in transportation and holding costs on the supply chain. By evaluating how inventory and shipment patterns adapt to cost fluctuations, we identified key cost drivers. The sensitivity analysis highlighted the most influential factors in the network, offering valuable insights for cost optimization. Future iterations of the model could integrate carbon cost constraints, promoting more sustainable practices. By optimizing inventory levels, the model helps reduce waste and overproduction, contributing to a more efficient and eco-friendly supply chain. Ultimately, the model supports environmentally conscious decision-making and aligns with sustainability goals. This model showcases strong potential for real-time optimization in industrial environments. It supports improved strategic planning and boosts operational efficiency. Its scalable design makes it adaptable to complex global supply networks, and it lays a solid foundation for incorporating uncertainty and dynamic factors in future developments. To enhance the supply chain model, we plan to integrate real-time data feeds for dynamic decision-making, expand the model to include multiple supplier tiers and additional constraints, incorporate stochastic elements to better capture uncertainty, and introduce sustainability metrics to assess environmental and social impact. These improvements will make the model more adaptive, realistic, and aligned with long-term strategic goals. In conclusion, the model effectively balances production, inventory, and distribution across the supply chain. The optimization framework enables informed decision-making within real-world constraints, demonstrating the practical value of mathematical programming in driving efficiency and strategic planning in supply chain management.